Right. I personally really dislike 2.49 because it is conceptually very simple. I would almost say trivial in some ways. But mathematically, this is probably one of the harder problems in the textbook, at least for Chapter 2. And I really don't like that because really it starts leaning more towards math instead of physics when we start having problems like these, but regardless. In Part A, we are given this really messy wave function, and we want to show that this does, in fact, satisfy the time-dependent Schrodinger equation for the harmonic oscillator potential, where x0 is just some random real constant with dimensions of length. So, for reference, the Schrodinger equation, the time-dependent Schrodinger equation, is defined as I h bar times the partial of psi with respect to time being equal to the negative h bar squared over 2m times the second partial of psi with respect to x plus the potential v multiplied by psi. Now, for a harmonic oscillator, we have v being equivalent to 1/2 m omega squared x squared. So if we plug that in to here as 1/2 m omega squared x squared multiplied by psi. And then now we want to show that this wave function here that we've given satisfied this. So all this is for part A is a matter of plugging this into the Schrodinger equation and verifying that this is actually correct. Now, that is easy to understand how to do this problem. The actual math is a lot harder because we have to take the first derivative of psi with respect to time and the second derivative of psi with respect to x. And this is a very messy expression. So let's do this one by one, starting with the partial of psi with respect to x. So let's do this in red. Starting with d psi by dx, this is going to give us, let's see, we have m omega over pi h bar to the power of 1/4, which comes out as a constant at the front. And then we have our exponential, which doesn't change. So negative m omega over 2h bar multiplied by x squared plus x naught squared over 2 multiplied by 1 plus e to the negative 2I omega t plus I h bar t over m minus 2x naught x e to the negative I omega t. And let's see, here everything is once again capped off, and then close this. So we have this exponential, and then we have the derivative of this inner term. So that's going to give us, let's see. So this is going to be multiplied by dx of negative m omega over 2h bar x squared plus, and for just to make this a little bit faster, I'm going to just ignore all of the terms that don't have x components to them, because once again, derivatives of constants are just 0, respectively. So this middle term is going to be minus m omega over 2h bar multiplied by x naught squared over 2 times 1 plus e to the negative 2I omega t. That just derives to 0 based on x, so I'm just going to ignore that term. Same thing with the I h bar t over m multiplied by negative m omega over 2h bar. There's no x here, so that goes to 0 as well. Our final term is going to be negative m omega over 2h bar multiplied by negative 2x naught x e to the negative I omega t, so I'm going to include that one, plus m omega over h bar, because the 2's cancel out, multiplied by x naught times e to the negative I omega t multiplied by x. So at this point, then we get that the partial of psi with respect to x is equivalent to, and we can factor out an m omega over h bar. In fact, let's factor out a negative m omega over h bar. So this is going to be m omega over pi h bar to the power of 1/4 times exp. And you know what? I don't even know why I'm doing this when I can just copy paste the front line. Like this. So we have everything from the front, and then now we're multiplied by negative m omega over h bar multiplied by dx of 1/2 x squared minus x naught e to the negative I omega t multiplied by x. And if we actually carry out this derivative, this is going to give us x minus x naught e to the negative I omega t, which means that the final derivative expression is going to be d psi by dx is equivalent to this same expression at the front. And let's multiply this by negative m omega over h bar, and then multiply it by x minus x naught e to the negative I omega t. And this is our first derivative. So now let's take the second. Okay, now let's take the second derivative, and we're going to take advantage of product rule here. So let's see. The second derivative of psi with respect to x is going to be, and we're going to bring the m omega over pi h bar to the power of 1/4 out. And then via product rule, we have d by dx of exp negative m omega over 2 h bar x squared plus x naught squared over half 1 plus e to the negative 2I omega t plus I h bar t over m minus 2 x naught x e to the negative I omega t multiplied by negative m omega over h bar times x minus x naught e to the negative I omega t. And then we're adding this with m omega over pi h bar to the power of 1/4 times exp negative m omega over 2 h bar x squared plus x naught squared over 2 1 plus e to the negative 2I omega t plus I h bar t over m minus 2 x naught times x e to the negative I omega t. Close this off, and then the derivative d by dx of negative m omega over h bar times x minus x naught e to the negative I omega t. So this is via product rule. So let's see, this is going to give us the first derivative, d2 psi by dx squared, being equal to m omega over pi h bar to the power of 1/4. And then we have the same, this derivative is going to give us the exact same expression on the right here. So we have the exponential negative m omega over 2 h bar times x squared plus x naught squared over 2 times 1 plus e to the negative 2I omega t plus I h bar t over m minus 2 x naught times x e to the negative I omega t. Cap this off, close off the exponential, and then we have m omega over h bar squared now times x minus x naught e to the negative I omega t, this time squared. At the bottom, we have plus m omega over pi h bar to the power of 1/4, and then the same exponential, which I really don't want to write anymore, so I'm just going to copy paste, which is probably what I should have done at the very start, multiplied by the derivative, which is going to give us, let's see, negative m omega over h bar multiplied by 1 minus 0, so actually just multiplied by 1. And then we can use a bit of distributive property here, and we get d2 psi by dx squared is equal to, and we can factor out m omega over pi h bar to the power of 1/4 multiplied by this exponential. And then we're going to be multiplying this by, let's see, the first term is going to be m omega over h bar squared times x minus x naught e to the negative I omega t squared. And then at the bottom, we're going to be adding, or in this case, subtracting m omega over h bar. So this distributed term, let's see, is going to simplify a little bit. This is going to be m omega over h bar squared multiplied by, let's see, x minus x naught e to the negative I omega t times x minus x naught e to the negative I omega t. This is going to be x squared minus x naught, yeah, minus 2x naught x e to the negative I omega t plus x naught squared e to the negative 2 I omega t, subtracted by m omega over h bar. And let's see, I might be able to rearrange this a little bit. Yeah, so this is, I can rearrange this just to move up the constants to the front. So it's going to be negative m omega over h bar plus m squared omega squared h bar squared x squared, subtracted by 2m squared omega squared x naught e to the negative I omega t divided by h bar squared, multiplied by x, and then finally added with m squared omega squared x naught squared e to the negative 2 I omega t, all divided by h bar squared. Is that correct? Yes. Okay, yeah, and that's our second derivative. So if I want to write this out fully, then I'm going to get that it's equal to second derivative psi with respect to x squared is equivalent to this entire thing at the front, and then multiplied by negative m omega over h bar plus m squared omega squared over h bar squared times x squared minus 2m squared omega squared x naught e to the negative I omega t over h bar squared plus m squared omega squared x naught squared e to the negative 2 I omega t h bar squared again. And I messed that up. There we go. Okay, and that is our second derivative. Now we have to do the time partial. Okay, immediately, my apologies, I messed this up a little bit. There's supposed to be an x here that I forgot to include. But other than that, this is correct. So now let's do the partial with respect to time. So d psi with respect to t is going to equal, and we have the same m omega over pi h bar term at the front to the power of 1/4. And then, let's see, we're going to have, yeah, so the same exponential, which I'm going to just copy paste from here. You know what, let's move everything down so I'm not messing up the h bar on the second derivative with respect to x. And then we're multiplying by the derivative with respect to time of, let's see, so get rid of, once again, as before, get rid of all of the terms that don't have t's with respect to. So this is going to be negative m omega over 2 h bar times x naught squared over half 1 plus e to the negative 2 I omega t. That's one term that we're keeping. We're keeping this middle term as well, so minus m omega over 2 h bar times I h bar t over m. And then we're keeping this final term as well, so plus m omega over 2 h bar times 2 x naught x e to the negative I omega t. So now let's solve this derivative expression. So this is going to be d by dt, and we're going to simplify some stuff. So immediately, the thing I see is I can just cancel out the 1, because that one's not going to give me a t expression. So I'm going to get, finally, negative m omega x naught squared over 4 h bar times e to the negative 2 I omega t. Over here we have the m's that cancel out, so it's going to be minus I omega h bar over 2 h bar. And you know what? The h bars also cancel out. So what we're left with is minus I omega over 2 multiplied by time. And then over here, the 2 cancels out with this. I believe that's it. So plus, let's see, m omega x naught x over h bar e to the negative I omega t. Is that correct? X naught x e to the negative I omega t h bar on the bottom, yeah. Okay, and then if we derive this, this is going to give us, let's see, negative m omega x naught squared over 4 h bar multiplied by negative 2I omega times e to the negative 2I omega t minus I omega half plus m omega x naught x over h bar multiplied by a negative I omega times e to the negative I omega t. If we simplify this a little bit, then this is going to give us, let's see, I m omega squared x naught squared over 2h bar. Is that correct? Because the two negatives cancel, the 2 cancels out and makes a 2 at the h bar. 2h bar at the bottom, we have I m omega squared x naught squared, and then e to the negative 2I omega t, subtracted by I omega over 2, and then over here we have minus I m omega squared x naught x over h bar e to the negative I omega t. So then we take all this and we just replace the bottom with it. So we have the derivative with respect to time. Let's erase out the stuff that we accidentally copy pasted over. And we're multiplying by this term that we just derived out. So this is going to be multiplied by I m omega squared x naught squared over 2h bar e to the negative 2I omega t minus I omega over half minus I m omega squared x naught times x divided by h bar e to the negative I omega t. And let me just double check that that is in fact correct. Minus I m omega squared x naught I omega t h bar, and then I m omega squared x naught squared e to the negative 2I omega t over 2h bar. Yeah, okay, that's correct. And so we've finished these 3 derivatives. Now we can plug them into the Schrodinger equation. Okay, so now we actually have to verify that both sides of this equation evaluate to the same result. So let's do the left first, and we'll do this in blue. So I h bar multiplied by the partial of psi with respect to time. So that's just taking this expression and multiplying I h bar. So we get, you know, the same m omega over pi h bar to the power of 1/4 term at the front, our exponential, which doesn't change, negative m omega over 2h bar, x squared plus x naught squared over 2 times 1 plus e to the negative 2I omega t, plus I h bar t over m minus 2 x naught x e to the negative I omega t, close out the exponential, and we're multiplying I h bar. So what we're going to get at the bottom is going to be, let's see, so I h bar multiplied by this first term is going to give us, the 2 i's make a negative, so we have negative, the h bars cancel out, so we have negative m omega squared x naught squared over 2 times e to the negative 2I omega t. Over here, the 2 i's cancel and make a positive, so plus omega h bar over 2. Same thing here, the 2 i's cancel, make a plus, the h bar goes away, so we get plus m omega squared x naught x e to the negative I omega t. And let me just double check that this is in fact correct. M omega squared x naught e to the negative I omega 2 t minus m omega squared x naught squared e to the negative 2I omega t over 2. Okay, yeah, that's correct. Next thing is going to be this expression over here. So this one's a little bit harder, so let's do that separately. Okay, so starting with this first expression, which I'm going to write in purple. So negative h bar squared over 2m times the second derivative of psi with respect to x squared is going to equal. So we have, let's see, I'm going to absorb the negative term into sort of the parentheses over here. So we're going to get the same sort of expression at the front, which is going to be m omega over pi h bar to the power of 1/4 exp of negative m omega over 2h bar x squared plus x naught squared over 2 times 1 plus e to the negative 2I omega t plus I h bar t over m minus 2 x naught times x e to the negative I omega t. And then now we multiply. So we're multiplying negative h bar squared over 2m. So negative h bar squared over 2m multiplied by this parentheses expression right here, which I'm actually just going to copy paste over because I want to write this in 2 lines. So this is going to give us, I'm going to start by copy pasting this top term. And then we're multiplying by, so the first term becomes positive, and we have, let's see, the m's cancel out, we get h bar omega over 2, I believe. H bar cancels with that, the 2 positives, omega over 2, yeah. And then we're subtracting, the h bar squares cancels out with the h bar squared at the bottom, one of the m's cancels out, we have m omega squared over 2 times x squared, I believe. 2 m omega squared x squared, yeah. And then over here, the 2 minuses make a positive, and I just realized the h bar squared got cut off again. So, okay, this third term, 2 negatives make a positive, h bar squared cancels out at the top, the 2m cancels out at the bottom to make m omega squared x naught e to the negative I omega t multiplied by x. Is that correct? H bar squareds cancel, 2 m's, we get m omega squared x naught e to the negative I omega t x, yeah? And then subtracted by, and we have 2 h bar squares that cancel again, and we get at the top m omega squared x naught squared e to the negative 2 I omega t, and at the bottom we get a half. Okay, next term, 1/2 m omega squared x squared psi, which let's write in green. So that's going to be 1/2 m omega squared x squared psi, which is going to be equal to the wave function itself multiplied by just that. So m omega over pi h bar to the power of 1/4 exp negative m omega over 2 h bar times x squared plus x naught squared over 2, 1 plus e to the negative 2 I omega t plus I h bar t over m minus 2 x naught times x e to the negative I omega t. And then we're just multiplying by 1/2 m omega squared x squared. So if we plug all of these back into the Schrodinger equation, immediately the first thing I realize is that every single term here shares a factor of sort of this m omega over pi h bar to the power of 1/4 times the exponential. So what I can do is I could just take this and cut out this from every expression. So what I have left is going to be, let's see, this expression is going to be equal to the purple expression and I believe it's added, yeah, added with the green expression. So what we're trying to do is we're just trying to verify that this is actually true. So let's see. We have 1/2 m omega squared x squared, and we have a negative 1/2 m omega squared x squared. So this is actually just going to equal h bar omega over 2 plus 1/2 m omega squared x squared plus m omega squared x naught e to the negative I omega t times x minus m omega squared x naught squared e to the negative 2I omega t over half. And then immediately I see here that we share another common factor, m omega squared x naught e to the negative I omega t. Actually, you know what? This doesn't share an x factor at all. Actually, my bad. So let's see. Plus 1/2, that's correct. M omega squared x naught x e to the negative I omega t. Ah, that's where I made my mistake. My apologies. It's not that these two add to this, it's these two just straight up cancel out. So there's actually, this term doesn't exist. Sorry about that. So what we have now is, let's see. this term matches this term matches this term, and then this term matches this term. So, and the signs all match as well. So every term here has an adjacent term here. This left expression is exactly equal to this right expression. Therefore, the Schrödinger equation is satisfied, and we have finished part A, which is to show that this is in fact a valid solution for the time-dependent Schrödinger equation for the harmonic oscillator potential. So we're done with part A, and we move on to part B. Okay, part B, we want the magnitude squared of this expression. So we have psi defined as m omega over pi h bar to the power of 1/4 times the exponential of negative m omega over 2h bar multiplied by x squared plus x naught over half 1 plus e to the negative 2I omega t plus I h bar over m minus 2 x naught x e to the negative I omega t. Close this off at the bracket. And then we have the complex conjugate, psi star, being m omega pi h bar to the power of 1/4 exp negative m omega over 2h bar multiplied by x squared plus x naught squared, I forgot the squared here, over 2, 1 plus e to this time 2 positive 2I omega t minus I h bar, and I left out the t here by accident as well, over m minus 2 x naught times x e to the positive I omega t. So if we want to find the magnitude squared of this expression, this is equal to psi multiplied by psi star. This is going to give us square root of m omega over pi h bar multiplied, I'm going to write this on the new line, exp of, let's write this out fully. So negative m omega over 2h bar x squared minus m omega x naught squared over 4h bar times 1 plus e to the negative 2I omega t minus I h bar omega t over 2h bar, and actually the h bars cancel out as well. So I omega t over 2. Let me just double check that that is in fact correct. The m cancels out, the h bar at the bottom cancels out, so we have I omega t at the top and then 2 at the bottom, yeah. And then plus, let's see, the 2 cancels out, so we have m omega x naught x e to the negative I omega t, all divided by h bar. And then we're adding on this bottom expression, so we're going to be minus m omega over 2h bar times x squared minus m omega x naught squared over 4h bar times 1 plus e to the positive 2I omega t. Let's see, this time plus, once again, the h bars and the m's cancel, so I omega t over 2 this time. Is that correct? M's cancel, h bars cancel, I omega t over 2, yeah. And then added with m omega x naught x e to the positive I omega t, all divided by the 2's cancel, leaving only an h bar. So let's see, immediately these two terms cancel out, so the magnitude of psi squared is now going to equal the square root of m omega over pi h bar times the exponential of, let's see, these two terms add, so we're left with minus m omega over h bar times x squared. That gets rid of these two. We have minus m omega x naught squared over 4h bar times 1 plus e to the negative 2I omega t, subtracted by m omega x naught squared over 4h bar 1 plus e to the positive 2I omega t, and then added with m omega x naught x e to the negative I omega t over h bar, added with m omega x naught x e to the positive I omega t over h bar. And now, let's see, we can start taking advantage of, let's see. Yeah, at this point, we can start taking advantage of distributive property once again. This is going to give us the magnitude of psi squared being equal to the square root of m omega over pi h bar. And then our exponential, and let's start distributing out. So we have negative m omega over h bar times x squared minus m omega x naught squared over 4h bar multiplied by 1 plus e to the negative 2I omega t. Let's see, plus 1 plus e to the 2I omega t. Is that correct? Yes, that is. Okay. And then finally, plus m omega x naught x over h bar times e to the negative I omega t plus e to the I omega t. Cap this off. And at this point, we can start taking advantage of the fact that these look very similar to trigonometric properties. Because remember, we can convert between complex exponentials and standard trigonometric functions. And that actually might make our resulting expression a little bit simpler. So magnitude psi squared is equal to square root m omega over pi h bar. Our exponential, negative m omega over h bar x squared minus m omega x naught squared over 4h bar times 2 plus e to the negative 2I omega t plus e to the 2I omega t. Plus m omega x naught x over h bar times e to the negative I omega t plus e to the positive I omega t. And now let's invoke trigonometric functions. So let's see. Over here we have e to the 2I omega t plus e to the negative 2I omega t. So immediately, I'm going to write this in red. I know that cosine of x can be expressed as e to the ix plus e to the negative ix, all divided by 2. So in the same way, I can say, okay, well, I know that 2 cosine of x is going to equal e to the ix plus e to the negative ix, which means that this expression over here is going to turn into 2 plus, let's see, 2 cosine of 2 omega t. Yeah. Similarly, on this side, we're going to get a 2 cosine of omega t instead of 2 omega t. Let's see. Let me just double check that that is in fact correct. Yeah. So our final expression is going to look something like magnitude psi squared equal to square root of m omega over pi h bar times the exponential negative m omega over h bar x squared minus, and I'm going to factor out the 2, so I'm going to get minus m omega x naught squared over 2 h bar times 1 plus cosine of 2 omega t plus 2m omega x naught x over h bar cosine of omega t. And let's see. At this point, I can factor out some stuff. Let's factor out an omega, m omega over 2 h bar. So if we do that, then we're going to get that this is actually equal to the square root of m omega over pi h bar. The reason why I'm factoring out m omega over 2 h bar is because I really want to get this term out outside of sort of the 1 plus cosine 2 omega t, just to make everything a little bit neater. So I'm going to get negative m omega over 2 h bar, and this is going to give me, let's see, 2x squared plus x naught squared times 1 plus cosine 2 omega t, and then subtracted by 4x x naught times x divided by, no, not divided by, there's no h bar anymore, and then multiplied by cosine of omega t. And at this point, I am technically done. However, I can simplify this a little bit more using double angle formula. So let me pull that up. because remember that cosine of 2x is equal to cosine squared of x minus sine squared of x, which is also equal to 1 minus 2 sine squared of x, which is also equal to 2 cosine squared of x minus 1. So at this point, if I want to simplify this even further, I can take advantage of double angle formula, and I can rewrite 1 plus cosine of 2 omega t to equal 1. Let's do the cosine term. So 1 plus 2 cosine squared of omega t minus 1, aka 2 cosine squared of omega t. So at this point, I'm going to get square root m omega over pi h bar times the exponential. Once again, negative m omega over 2h bar, 2x squared plus x naught squared, and then 2 cosine squared of omega t minus 4 x naught x cosine of omega t. And let's see, at this point, simplify this even more. Square root m omega over pi h bar exp negative m omega over h bar. And actually, I can actually pull the 2 back in now to get x squared plus x naught squared cosine squared omega 2, or omega t, minus 2 x naught x cosine of omega t. And if I want to make this even simpler, let's see. Yeah, so this can actually be simplified even more because this is actually a binomial. You can rewrite this as just x minus x naught cosine of omega t squared. Because you can double check this in reverse. You'll get x squared minus 2 x naught cosine omega t plus x naught squared cosine squared omega t if you multiply out this binary, which is exactly what you'll get here. So we can now fully do this to give square root m omega over pi h bar times the exponential negative m omega over h bar, and then multiplied by x minus x naught cosine of omega t squared. And you don't really have to do all of this. Technically, at this point, once you're here, you're basically done. You have the answer already. You can just graph this according to what the problem said, which is to describe the motion of the wave packet. You could just plug that into Desmos, but this is just easier to write and also easier to plug into Desmos when we actually do plug it into Desmos as well. So if I do that, what I'm going to get, if I just copy paste, if you were to plug this into Desmos, what you'll find is that this takes on the shape of something like a bell curve, and the bell curve turns out to oscillate with respect to time. So here we have the bell curve initially starting on the right at t equals 0, and we see as t goes to 1 with this specific choice of constants. You can choose whatever constants you want and just analyze what happens to the wave function as t goes up. But what will happen is that t, on this specific example, as t goes to 1, our bell curve gradually moves to the left, and as we sort of can keep on going, as we go starting from 1, this time on this new graph, on the left, as we go from 1 to 2, it goes all the way to the right again. So once again, this graph specifically chooses m omega and x naught to equal specific values. You don't really have to do that. You can have it so that m omega and h bar always equals 1, and just like assign random constants to omega and stuff as you graph this out. And then the only thing that'll change is that the rate of the oscillation will be different. So like the amount of time it takes for the bell curve to go from the right to the left, instead of being exactly equal to 1, will be some other arbitrary value. But regardless, no matter what sort of constants you choose, the bell curve will always sort of oscillate left and right, back and forth, effectively. Okay, part C. which I would feel is probably the most annoying part of this problem. Compute the expectation values of x and p and check that Ehrenfest's theorem is satisfied. So let's start by calculating the expectation value of x. So that's going to be equivalent to the integral from negative infinity to positive infinity of mag psi squared multiplied by x dx. Thankfully, we have the magnitude of psi squared from part b, so this is going to be just equal to the integral from negative infinity to positive infinity of x times the square root of m omega over pi h bar times the exponential of negative m omega over h bar times x minus x naught cosine of omega t squared dx. Now, obviously, this really isn't the most easy thing to actually integrate. And honestly, at this point, I feel like it would be valid for you to just plug this into an integral calculator and have it do it for you. But to actually solve this, what we can do is we can use u substitution, and we can make this a little bit simpler by saying, okay, I'm going to set u to be equal to x minus x naught times cosine of omega t. And by this logic, since x naught is a constant and omega and t have no dependence on x, du by dx is going to equal just dx. So du is going to equal dx. And then similarly, if we want to reverse this relation, x is then going to be equal to u plus x naught cosine of omega t. So if I plug this back into my expectation value integral, then I'm going to get that the expectation value of x is equal to, and I'm going to pull out the square root of constant, square root m omega over pi h bar. And I'm left with an integral from negative infinity to positive infinity, replacing x with u, u plus x naught cosine of omega t, times the exponential of negative m omega over h bar u squared dx. And at this point, I can then use the distributive property and say that this is equal to the square root of m omega over pi h bar times the integral from negative infinity to infinity of u e to the negative m omega over h bar u squared, and I'm going to switch dx to du directly, plus the integral from negative infinity to positive infinity of x naught cosine of omega t e to the negative m omega over h bar u squared du, cap everything off with brackets like this. Okay, at this point, we can recognize that this first function over here, u e to the negative m omega over h bar times u squared, this is an odd function because f of x is equal to negative f of x is equal to the negative of f of negative x. So because of that, and the fact that this is a symmetric integral means that this term is automatically just equal to 0. Because remember, an even sort of the symmetrical integral of any odd function is always going to be 0, because f of negative u is going to be exactly equal to negative f of u. So because of that, for every positive term in this integral, we have an equal matching negative term in the resulting summation. So because of that, everything cancels out. So because of that, we only have to worry about this rightmost term. So we're going to get square root m omega over pi h bar times x naught times cosine of omega t times the integral from negative infinity to positive infinity of e to the negative m omega over h bar u squared du. And at this point, once again, note that this is an even function. So at this point, we can rewrite this as 2 square root m omega over pi h bar x naught cosine omega t, going from the integral from 0 to infinity e to the negative m omega over h bar u squared du. And at this point, let's see, we can, this is basically a Gaussian, and if you don't remember how to do a Gaussian, look back on chapter 1. There are plenty of problems that involve practice with how to do these Gaussians. For my purposes, I'm just going to shove this into an integral calculator, e to the power of negative m omega u squared over h bar with respect to du going from 0 to infinity. And this resulting integral is going to give me 2 square root m omega over pi h bar times x naught cosine of omega t multiplied by square root of pi h bar over 2 square root of m omega. So the pi h bar and m omegas all cancel, the 2's cancel. This gives us a final result of x naught cosine omega t. Remember, once again, this is a Gaussian integral. At this point, I'm too lazy to actually do the calculation by hand, but you should know how to do this by hand. So if you don't remember how to actually calculate a Gaussian without consulting an integral table or integral calculator, I would highly recommend you go back and look at the problems in chapter 1, where they sort of go over this in one of the very early problems. I believe within the first 10 problems they will go over the Gaussian in chapter 1, so look back there if you're not comfortable with actually how solving this works. Okay, the significantly harder one of the two, the expectation value of p, is going to equal the integral from negative infinity to positive infinity of psi star multiplied by the p hat operator, negative I h bar d by dx, multiplied by psi, closed with dx. So this is actually equal to negative I h bar, integral from negative infinity to positive infinity of psi star times d psi by dx. Now, if you remember back in part A, we solved for d psi by dx when we were verifying the Schrodinger equation, and we found that it was equal to this expression. So if we plug this back in and also recognize what psi star is going to equal, right? Let's see. Psi star is going to equal m omega over pi h bar to the power of 1/4 times the exponential of negative m omega over 2 h bar times x squared plus x naught squared over 2 times 1 plus e to the positive 2I omega t minus I h bar t over m minus 2x naught times x e to the positive I omega t. If we take these and multiply them together, we're going to get this is equal to negative I h bar, the two constants at the front, which become square root m omega over pi h bar, times the integral from negative infinity to infinity of the exponential, and this is a bit of a doozy, so let's see. And exponentials multiplied together have their exponentials add, so we have negative m omega over 2 h bar times x squared minus m omega x naught squared over 4 h bar times 1 plus e to the 2I omega t minus m omega x naught squared for h bar, yeah, plus, what's this going to be? M's cancel, h bars cancel. This is going to be I omega t over 2, I believe. Let me just double check that. M's cancel, h bars cancel, I omega t over 2, yeah. And then added with 2 cancels out, m omega x naught x e to the I omega t, all divided by h bar. Is that correct? Yes. And then on the lower side, we are, let's see, we're subtracting once again m omega over 2 h bar x squared minus m omega x naught squared over 4 h bar 1 plus e to the negative 2I omega t. And then we are subtracting, this time, I omega t over 2. Is that correct? Yeah. And then we're adding m omega x naught x e to the negative I omega t all divided by the m cancels. We're left with an, let's see, oh sorry, the 2 cancels and we're left with an h bar at the bottom. And I made a mistake here. This is supposed to be a subtraction term, I believe. Is that correct? No, it is addition. Yeah, okay. And everything closes off. And then finally, we're multiplying by a factor of negative m omega over h bar times x minus x naught e to the negative I omega t. And we're closing everything off with a dx. So immediately I see that these two terms cancel out. And what are we left with? We get, I can bring the negative m omega over h bar to the front. So I get I h bar m omega over h bar, square root of m omega over pi h bar, times the integral from negative infinity to positive infinity of the exponential of, let's see, these two terms add, we get negative m omega over h bar x squared minus m omega x naught squared over 4 h bar times 1 plus e to the 2I omega t minus m omega x naught squared over 4 h bar 1 plus e to the negative 2I omega t. And then plus m omega x naught x over h bar e to the I omega t plus m omega x naught x over h bar e to the negative I omega t. And then all of this is going to be multiplied by x minus x naught e to the negative I omega t dx. So then we use a little bit of distributive property and also cancellation. The front here, the h bars cancel, we get I m omega root m omega over pi h bar multiplied by the integral from negative infinity to infinity of the exponential of negative m omega over h bar x squared minus m omega x naught squared over 4 h bar times 2 plus e to the 2I omega t plus e to the negative 2I omega t, and then added with m omega x naught x over h bar times e to the I omega t plus e to the negative I omega t. Close this off and we're multiplying by x minus x naught e to the negative I omega t dx. So at this point, we're going to do the same thing that we did back in part A, which is we're going to start taking advantage of conversion identities between complex exponentials and traditional sinusoids, because isn't necessarily the neatest thing in the world to have these complex exponentials in our equations. So if we do that, let's see, we can use the properties that sine of x is equal to e to the ix minus e to the negative ix over 2, and cosine of x is equal to e to the ix plus e to the negative ix over 2. So if we look here, we have, e to the ix with x being 2 omega t plus e to the negative ix. So we can rewrite this as e to the 2I omega t plus e to the negative 2I omega t is actually equal to 2 times cosine of 2 omega t. If that's correct. Is that correct? 2 omega t. 2I omega t. Yeah. And then e to the I omega t plus e to the negative I omega t is going to equal to cosine of just omega t. So if we rewrite it this way, then the expectation value in P is going to equal I m omega over the square root of m omega over pi h bar times the integral from negative infinity to positive infinity of the exponential negative m omega over h bar x squared minus m omega x naught squared over 4 h bar multiplied by 2 plus 2 cosine of 2 omega t plus m omega x naught x over h bar times 2 cosine of omega t, and all of this is multiplied by x minus x naught e to the negative I omega t, close off with a dx. I can distribute out some stuff, turn these 2's into 1's, get a 2 out at the front, which cancels with the 4 at the bottom, making a 2 at the bottom. And let's see. At this point, I should be able to pull off sort of the same cancellations I've been doing earlier in part C. Let's see. Yeah, so once again, this looks exactly sort of like the expression that we have in part A when we were solving for sort of the, or not part A, in part B when we were solving for the magnitude squared expression, this exponential here. So we already know how to simplify this. We can pull out some common factors, and we can effectively rewrite this as an exponential of negative m omega over h bar multiplied by x minus x naught cosine omega t squared, and then multiplied by x minus x naught e to the negative I omega t, closed off with a dx. So if you don't remember how I did this, go back to part B where we found the magnitude squared. We had this exact same expression there, and we simplified it by first taking advantage of the double angle identity for cosine 2 omega t, and then distributing out this negative m omega over h bar, and recognizing that the final sort of result was a binomial that could be rewritten as, or the final result was a polynomial that could be rewritten as the square of a binomial like this. So look back at part B if you don't remember how that substitution went, because I'm literally taking it exactly from there, because this is the exact same expression, this exponential. The only difference is that there's this extra multiplicative factor at the front, which is what appears here. So at this point, we're going to once again use u sub. So I'm going to say u is equal to x minus x naught cosine of omega t, which means that du is just equal to dx, and x is equal to u plus x naught cosine of omega t. And at this point, the expectation value of p is then going to equal I m omega times the square root of m omega over pi h bar, multiplied by the integral from negative infinity to positive infinity of the exponential negative m omega over h bar, multiplied by u squared, and then this time multiplied by u plus x naught cosine omega t minus x naught e to the negative I omega t, closing off with a du. So at this point, I'm going to distribute this out. So this is going to give me I m omega times the square root of m omega over pi h bar times the integral from negative infinity to infinity of u e to the negative m omega over h bar times u squared du, plus the integral from negative infinity to infinity of x naught cosine of omega t e to the negative m omega over h bar u squared du, minus the integral from negative infinity to infinity of x naught e to the negative I omega t e to the negative m omega over h bar u squared du. So once again, for the same reason, this is an odd function. This is a even integral or symmetrical integral. As a result, this is automatically equal to 0. And then let's see. Over here we have x naught cosine of omega t plus, yeah, so we can actually combine this together. So I made a bit of a mistake here separating them. So this is actually equal to I m omega square root m omega over pi h bar times the integral from negative infinity to infinity of x naught cosine omega t plus x naught e to the negative I omega t multiplied by e to the negative m omega over h bar u squared du. And I see that I have both complex exponentials and sinusoids in this expression. So I'm going to do the basic thing where I'm going to turn this into a sinusoid. So if I do that, let's see. Red, e to the negative I omega t via Euler's identity is going to be cosine of omega t minus I sine omega t. So, let's see. That's where I went wrong. Apologies. I didn't carry over the subtraction here. So this is actually supposed to be a minus. So if I do that, then at this point, if I plug this back in, I'm going to get I m omega root m omega over pi h bar, integral from negative infinity to infinity of x naught cosine omega t minus x naught cosine omega t plus I x naught sine omega t. All this multiplied by e to the negative m omega over h bar u squared du. So the two cosines cancel out to 0, and we're left with negative m omega root m omega over pi h bar times x naught sine of omega t times the integral from negative infinity to infinity of e to the negative m omega over h bar u squared du. And once again, we have this exact same Gaussian integral that we had from earlier on. So once again, I'm going to plug this into my integral calculator because I'm too lazy to actually do this by hand, since it is a Gaussian, which is kind of tedious to do. This is going to give me that this expression is equal to square root pi h bar over 2 square root m omega. So this conveniently cancels out exactly with this, and we're left with, and let's write this down here, the expectation value of p is equal to negative m omega over 2 x naught sine of omega t. And let me just double check that this is in fact correct. Negative m omega x naught sine omega t. Okay, that's where I went wrong. Apologies. So this actually doesn't have a 2 because I did not set this, I did not multiply a 2 at the front and set this equal to 0 like I did previously. Here, I just evaluated it from negative infinity to positive infinity straight up without taking advantage of the fact that this is even and just attaching a 2 at the front and setting this equal to 0. So if I actually did the integral like this, the result would not have a 2 at the bottom. So actually, it's not supposed to have this 2 here. So that's my mistake. But this is indeed the final value for the expectation value of p. Okay, finally, we want to check the Ehrenfest theorem, which states that the derivative of the expectation value of p with respect to time has to equal the expectation value of negative dv by dx. So for our harmonic oscillator, we have v set equal to 1/2 m omega squared x squared. So dv by dx is going to equal m omega squared x, and the negative of that is just going to be this. So the expectation value of negative dv by dx is going to equal negative m omega squared times the expectation value of x, which is going to be x naught cosine of omega t, and derivative of p with respect to t is going to equal negative, let's see, m omega squared x naught cosine of omega t, where I'm taking the derivative of this thing with respect to time to get this. These are indeed equal, therefore Ehrenfest theorem is indeed verified, and with that we are finished with this problem.